Okay, so I think we're about 4 after, so we'll get started here. Welcome everyone to the June TEPS seminar. Today we have 2 TEPS trainees, Justin Kerr from York University and Pierre-Alexis Roy from the University of Montreal presenting. We'll just get started. So I'll pass this off to Haley Sapers to introduce Justin Kerr.
Good afternoon, everyone. Thanks for the opportunity to introduce Justin. I've had the pleasure of working with Justin Kerr for the past couple of years in the Planetary Volatiles Laboratory. So Justin Kerr is a master's student in Physics and Astronomy, working under the supervision of Professor John Moores. Justin completed his BSc in Physics and Astronomy at York University in 2020, and Justin also holds a Bachelor's of Arts in History. Justin's current research focuses on the use of radiative transfer models for the Martian atmosphere to optimize solar panel positioning on surface missions. And so without further ado, I'm sure we're all looking forward to hearing about Justin's research advances. Thanks, Justin.
Thank you for the introduction, Haley. Okay, so it should be clear. All right, so today I'm going to be talking about investigating solar panel efficiency on Mars through the use of radiative transfer models. So why look at solar panel efficiency on Mars? Well, currently we consider solar energy to be one of the main power sources for operations on the Martian surface. As you can see here, I've shown a little graphic of some different Mars surface missions with the ones using solar panels circled. The other option, of course, would be nuclear-powered RTGs. However, there is a lot of difficulty with those with the availability of the isotopes, and especially for small-scale missions, say if you wanted to put weather stations across Mars, solar power is much more feasible. So currently, when planning missions, solar energy budget is only considered after location selection. So it would be purely science value for location selection, and then power budget would be considered afterwards. However, if we can have some consideration of energy availability during site selection, that may lead to some better options for site selection, where we may have much better power options for some locations with similar science value. Now, currently, data for different orientations of solar panels is only available for flat panels, so horizontal panels on the surface. There isn't currently global data available for panels at angles or facing in different directions. So this is something that we are currently looking to produce in a manner which could be accessed for a base introductory level during site selection. Of course, more detailed analysis for specific sites involving terrain, which could block light and such, would have to be carried out once you select a specific site. So solar panel effectiveness on Mars is dominated by incoming radiation rather than any environmental factors. So although, of course, temperature and humidity can be a concern, there are studies which have shown that it is massively dominated by just the amount of solar radiation reaching your panel. Therefore, optimizing the panel placement is a key aspect for the maximization of energy production on these surface missions. Now, of course, we can expect that sun tracking panels would provide the highest energy output by just following the sun, since you're always going to get the maximum amount of energy from that direct sunlight coming through the atmosphere if your panel's directly pointed at it. However, static panels are, even though they're less effective, they are much easier engineering-wise and cheaper to put on a rover, and would be less prone to engineering difficulties because there are just less moving parts, less weight for your space mission. So it can be much more essentially economically and engineering friendly to use a static panel instead of a sun tracking panel. So one thing we want to look at is just how much you're losing energy-wise by using such a static panel. And so this can be weighed against the increased costs of using a sun tracking panel. And here I've just given a diagram showing Mars throughout the year around the sun. which should give you some intuition for the amount of light reaching different areas of the planet, which we can move on to in a bit. So here's some information on the model that we're using to calculate the amount of energy available at the surface. So we use a one-dimensional radiative transfer model based on the works of Moores, Smith, and Sugar in 2017 and Smith and Morris 2020 to calculate radiation fluxes at the surface. So these models calculate direct and diffuse radiances throughout the Martian year at all latitudes, so we can get values across the entire planet. This adapts the doubling and adding method used by Griffiths et al. 2012 for use on Mars, because Griffith used this for Titan. And in turn, his work was based on the work of Tomasco et al. In several different publications, as well as the method first being used for this type of thing by Hansen in 1969. So how this doubling and adding code works is it computes radiative transfer by starting with thin infinitesimal layers of atmosphere, which would be thin enough to ignore multiple scattering of light as it goes through the atmospheric molecules. So what we can then do is, of course, do this so that we can have an easy time of getting transfer matrices throughout the atmosphere, instead of trying to do the entire thing at once and having to calculate every possible way, and essentially having to use something like Monte Carlo methods to get through this. So instead, we can do these thin layers and then double the layers such that we have two of them placed on top of each other, and then add the diffuse and direct radiation going through each at the boundary between the two. We can then do this with layers throughout the entire atmosphere, calculating the middle boundaries, and then integrate over all of them to acquire reflectance and transmittance matrices for light entering the top of the atmosphere as it would propagate down to the surface. Our model uses three main levels, with gaseous absorption occurring primarily in the top level, Mie scattering in the lower level, and some Rayleigh scattering throughout all three. So for investigating scattering and wavelengths in this, we calculate solar fluxes for wavelengths between 200 and 2000 nanometers, which accounts for about 93% of inbound solar flux at Mars. The 1800 to 2000 nanometer range is not actually required for the solar panel analysis due to just the efficiencies of the panels at different wavelengths, but we're still including it because it was used in previous works, and we'd like to have it there for validation. Now some more about why we chose these wavelengths is that only 0.007% of solar energy is available from wavelengths below 200 nanometers. So it would essentially be much more computational work for very little gain to include this. CO2 absorption is extremely high below 200 nanometers, which is, again, along with this. However, CO2 absorption is negligible between 400 and 1000, and we can ignore it completely. And oxygen absorption is only significant between 650 to 800 nanometers, where the model will include it. Everywhere else, it is low enough for us to ignore. And here we can see the breakdown of the atmosphere of Mars, as the carbon dioxide is the major component and is therefore one of the largest things we worry about. So for the analysis and validation processes, I developed analysis code to reformat the data and perform calculations of available energy based on various panel orientations. We then numerically integrate this solar panel flux over each day, where we have multiple sun positions throughout the day. The results were validated by calculating flat panel orientations and validating them against the Smith and Morris paper from 2020. And here you can see the outputs, the final outputs for the energy available per sol for a solar panel that is horizontal on the ground. And I should mention this is for 1 meter square panels. For slanted panels, we instead see some different results. For a fairly high tilt 60-degree panel, we would see much higher energy, as we'd see compared to A flat panel around the northern hemisphere, when the sun is, of course, over the southern hemisphere, is where we see the largest gains. And of course, we would see loss if you placed a panel such as this in many other areas. So we're seeing mostly gains in the northern hemisphere, as can be expected. And with a relatively severe 60-degree tilt upwards, this would be facing south. I've also performed this for different panel orientations as well. We could see here up to about 7 times the amount of energy being produced compared to a flat panel at high latitudes in the northern hemisphere. For a north-facing panel, you would see similar things, just inverted, with the southern hemisphere being the one where you're seeing good results. For lower tilt panels, we see much smaller ratios, of course. We see smaller gains for, say, a 15-degree panel compared to a 60-degree panel in that northern hemisphere region. However, still gains of about 2.5 times. So as we see, it's quite beneficial to use a slanted panel instead of a flat panel if you are high up in the northern hemisphere. Comparing some different angles. So here we have a 45 versus 15-degree panel facing south again. And we would see, again, about 3 times as much energy in this northern hemisphere area for that 45-degree panel compared to a 15. However, you would see a much deeper available region compared to the 60-degree one, where you would still get improved energy generation compared to the flat panel. A lot of this is due to the energy generation being dominated by direct radiance rather than the diffuse radiance from the atmosphere. So as soon as we start getting to areas where some of the sun paths are going to be getting your direct radiance coming behind the panel and losing it, you get large drops in energy availability. So a summary of what we did and some next steps. So we calculated solar flux at the surface of Mars using a 1D radiative transfer model. We analyzed the model data to investigate the effectiveness of different solar panel orientations and found that tilted panels were a significant improvement over horizontal panels at latitudes far from the equator. The tracking panel analysis is ongoing with just some minor code bugs still being worked out. And our next and final step with this is to calculate the quantum efficiency of the solar panels at each of our wavelength bands and convolve that into the data, which is currently essentially working without being put in, as the data has all been formatted to just require constant multiples applied in for the quantum efficiency. And that is what I have to show you today. Thank you very much. I should have time for questions if anyone has any.
Oh, there's a question from Logan.
Yeah, hi there. So recently I've been hearing about dust on the surface of Mars and how that's been impacting solar panels. So I'm just wondering if the tilt of these panels could have any impact on dust accumulation.
It certainly could. However, it's not something this analysis is looking into. As far as I know, most of it is more the wind that is the important factor for it, rather than the panel tilts. I believe there's a couple studies that have gone into that, but I am not an expert on it. It's something that we aren't considering in this run. But yeah, from what I've seen, there are some studies that look into it, and it is largely wind that is important for the accumulation, especially when we're probably talking at mostly places about non-severe tilt angles. Maybe if you put your panel at 90 degrees, but that might lead to some more difficulties.
Right. Yeah, makes sense. Thank you.
Do we have any other final questions for, Stefan?
Yeah, so I get that the moving panel would be more efficient over a static one. Is there worries about adding more moving parts and maybe then it
Right.
could more likely to break?
Yeah, that's exactly part of what motivates this, is that we know that there are a lot of troubles with adding in the moving panels. So like you say, there's many more points of failure with a moving panel. It'd also just be more expensive to develop, to put on a rover, likely heavier to have on your launch vehicle. So it's something where, that we see it, the tracking panels is likely much more complex and difficult to have. So what we want to do is say, if we can just have loss, really, is it compared to the solar tracking ones? Is it going to be even worth developing a tracking panel if it's only going to be a small percentage gain over something that's just sitting at 45 degrees? Because like you say, there's a lot of problems with tracking panels. So we want to show exactly how much of a loss it would be by not using one.
Parushan?
Thank you. Justin, I thought it was a great presentation. I think it's really cool that we're already looking at energy on Mars. That's awesome. So question for you, the doubling and adding code that you created, can you apply it to any planets with an atmosphere, or is there something unique about the code to Mars?
So it is workable on any atmosphere. So this code has actually been around. The base of this code is from the 90s. Some of the method is even in the 80s. It's been adapted many, many times. So we mentioned it was directly previous to our group taking this code on and adapting it for Mars. It was being used for Titan. Prior to that, it's been used on some different Mars stuff way back when, and I believe Earth as well, and some different stuff. But this method can be used for anything. The specific code is one that has been carried on throughout the years and used for different planets itself. There's just alterations you have to make when you want to adapt it to a new planetary body, of course. Things like amount of dust, seasonal variation in dust, atmospheric composition, all of these things are things that you have to alter. Certain things become more or less important depending on where it's being used. But the method is certainly usable on any planetary body with an atmosphere.
Awesome, thank you.
Welcome.
Do we have any final questions for Justin? Oh, well, thank you so much, Justin, for the presentation. Up next, we have Pierre-Alexis Roy, and introducing Pierre-Alexis, we have Stefan. So Stefan, take it away.
Thank you. It's my pleasure to introduce my friend and colleague, Pierre-Alexis Roy, who's also my office mate sitting behind me. Pierre-Alexis has been working with us as part of Professor Bjorn Benneke's exoplanet research group at the University of Montreal. Pierre-Alexis did his undergraduate obtained a bachelor's in honors physics and mathematics at McGill, graduated 2 years ago, and has since been a grad student with us. He started as a master's, but last year did a fast track into the PhD program. And today he'll be talking to you about his most recent paper submitted under review, talking about the sub-Neptune TOI 824. So take it away.
Thank you, Stefan, for the nice introduction. All right, so yeah, thank you very much for allowing me to share my work today on TOI 24b, which is a really nice and a really intriguing sub-Neptune, and a target that forces us to ask the question, are all sub-Neptunes really hydrogen-rich planets like we typically think of them? But I want to start with the planet that are closest to us in the solar system, since we know that we have the 4 rocky planets, and after that there are the 4 gas giants, or we can separate the gas giants and the ice giants in Neptune and Uranus, but basically 4 small rocky planets and 4 bigger planets with a lot of gas. And in between them, in between the Earth, which is the biggest rocky planet, and Neptune, which is the smallest of the gas-rich ones, there is not an interesting object. There's not a planet object that we can study. And for a long time, that was the picture we have of planetary bodies in our galaxy. But then exoplanet science became a huge field, and we were able to launch exoplanet transit surveys in the form of the Kepler mission, and then more recently the TEPS missions that had for objective to scan the sky and look at stars to find transiting exoplanets, so planets passing in front of their stars and giving us transit signals, allowing us to learn the radius of these planets. And here I'm showing an image which is the regions of the sky that were scanned by these missions. So the little yellow crosses are the Kepler fields, where it looked at the sky for a long period of time looking for these transits. And then these blue rectangles are the TESS views of the sky, which is rotating each 27 days and spending a month looking at the sky for transiting exoplanets. And these missions were really a huge success. The Kepler mission is now accountable for thousands of exoplanets we know of. There are still thousands that need to be confirmed. And the TESS mission is more recent, so there are only a few hundreds that have been confirmed, but there are thousands of candidates that need to be followed up for confirmation. And with these new thousands of exoplanets, we could now look at the size distributions of those planets. Is it the same thing as in our solar system? So here what I'm showing is the result from the Kepler mission, the number of planets per star as a function of the planet size. And the first thing we notice, first of all, there seems to be very few giant planets in these systems, and that the peaks of abundances in terms of the size of these planets is in between the size of the Earth and that of Neptune. So it's basically exactly the opposite as in our solar system. And the type of exoplanets that we see the most in our transiting surveys are absent from our solar system. So yeah, basically we call these planets super Earths and sub-Neptunes because it's the closest from the planets we know. And we make the distinction between these two peaks in this bimodal distribution because of this lack of observed planets around 1.8 Earth radii, which is called the radius valley, which is in itself another field of active research. But like I said, these super Earths, these sub-Neptunes, they are abundant. And despite that, we don't have a clear understanding of their composition and their formation history. But the typical image that we have when we think about these super Earths is that of a rocky planet with either a really thin or a missing atmosphere, kind of like just a scaled up version of the Earth. And for some Neptunes, we're going to look at them as these super Earths, but with an extended hydrogen atmosphere that's going to account for their larger volume. The thing is, these Neptunes, they're pretty hard to characterize in transit spectroscopy, which is our favorite method for obtaining abundances of small exoplanets. Because while they do have an extended atmosphere of hydrogen, at least we expect, and large atmosphere scale heights, which means that they would have large signatures in transit spectroscopy, most of these planets, they're rather cold, and it's favorable for clouds to form in their atmospheres. And this kind of mutes all of the features we're trying to look at during eclipses. Here I'm showing a famous example. It's GJ1214b, as seen with Hubble. And the transit spectrum we obtained, it's flat. And we think that's because of clouds in the atmosphere. Now, a way to work around this problem of having to deal with clouds is to look at the thermal emission that's directly coming from the planet. And we can do this during the eclipse of the planet, where it goes behind the star with respect to us, and we can isolate the thermal emission. And so here I'm showing a figure of the emission spectroscopy metric, which is just an index of how suited a planet is for eclipse observations. Basically, do we expect a high signal to noise or a low signal to noise ratio for eclipse observations? The thing is, in the sub-Neptune population, we see that we are kind of not finding a particularly good target to follow with this method. But this changed when TESS revealed a new target. So TOI 824b, it falls directly in the sub-Neptune population, and it's on a really short orbit of 1.4 days. with a really hot equilibrium temperature, which makes it radiate a lot of heat and makes it a good target for emission spectroscopy. So this is where it falls on the emission spectroscopy metric figure, and it becomes the most promising Neptune to follow up in eclipse. Not only is it particular because it's hot, it's also really massive. So here I'm showing TOI24b on a mass and radius diagram, and we see that compared to other sub-Neptunes that were characterized with Hubble in the past, for example, it's almost 3 times as massive. And this raises the question, what is TOI24b made of? What's this dense sub-Neptune object? And we can first approach this question on the mass radius diagram and compare it to theoretical composition curves. So we see that our TOI24b data point is consistent with either an Earth-like core with a 1% biomass hydrogen envelope, or with a 50-50 Earth-like core with a water envelope. And basically, we wanted to push this this reflection further. So we created a grid of models, of interior models of the planet, on which we added non-gray atmosphere models, and then we could compare our models to the physical properties of the planet observed to find this posterior distribution, which relates the hydrogen and helium mass fraction of the planet with the water mass fraction in the interior of the planet. And we see that basically the properties of TOI24b are consistent with a range of compositions that range from rock in a 1% hydrogen envelope up to a rocky core in a large water content mantle and almost no hydrogen. And basically, this first scenario is our typical image of a sub-Neptune. That's usually what we think of when we think about sub-Neptunes. But this other extreme, the one with a lot of water, it's kind of reminiscent of the composition of the mantle of Neptune in our solar system if we remove the hydrogen. So basically, this is now the question we are left with. What's the nature of TOI24b? Is it this hydrogen-rich super-Earth, this kind of typical sub-Neptune, or is it more of an exposed Neptune mantle with a lot of volatiles? And we know that it's a good idea to look at this planet in eclipse because of its high temperature. So that's what we did. We obtained 4 eclipses of TOI24b in each of the 2 Spitzer channels during the last month, I think, of its lifetime. And these are the light curves we obtained for TOI24b. If we now put these eclipse depths on a spectrum and compare it with atmosphere models for TOI24b, the first thing to note is that both these data points, these Spitzer eclipse depths, they are deeper than our atmosphere models if we assume the equilibrium temperature of the planet. So basically, we are not consistent with having just a uniform temperature around the planet, and we are basically observing a hotter day-side temperature for TOI24b. Again, we then did a Bayesian analysis, so we created a bunch of atmosphere models with varying bond albedo. This is the reflectivity index of the planet, and the heat redistribution factor, which describes how the heat is redistributed around the planet. Is it uniform, or are we looking at a hotter day side? And basically, we see that the high probability region is favoring a high heat redistribution factor, which counterintuitively means that it's a hotter day side. It emits like a bare rock, and a lower bond albedo. So we don't expect a lot of light to be just reflected right away by the atmosphere. So when we consider these findings in the context of these 2 scenarios that we're considering, if it were a rock in hydrogen, we would expect a hydrogen-dominated atmosphere. If we were looking at an exposed Neptune mantle, we would be expecting an atmosphere which is rich in metals. Now we don't have molecular information from the Spitzer observations, but we did observe this hot day-side temperature and these hints at poor heat redistribution. And we know from the literature and from 3D GCM simulations of sub-Neptunes that high melicity atmosphere leads to having these hot day-side temperatures and this great contrast between the day side and the night side on exoplanets, because these metal atmospheres have lots of opacity, and they raise the photosphere to layers in the atmosphere where the pressure is smaller and the radiative time scale is much smaller also. So basically the light when it enters the atmosphere, the heat is not redistributed, it's just re-radiated right away. And we wanted to test this. So we created 3D GCM simulations of TOI-24b for a low metallicity scenario with more hydrogen and a higher metallicity scenario. And we see that indeed with higher metallicity models, we are able to be consistent with the Spitzer observation, whereas in the hydrogen-rich scenario, we are not. So when we go back to our initial question, what's the nature of TOI-24b? Well, for now, these first few observations seems to be a first sign of evidence for TOI-24b being this volatile-rich exposed Neptune mantle with much less hydrogen than we usually think when we think about some Neptunes. In the future, this is a work that's going to need to be confirmed, and a really nice way to do this would be to use the James Webb instruments and do eclipse spectroscopy with TOI-24b, because like I said before, it's a really nice target to do eclipse observations. But moreover, we measured in this work a higher temperature on the day side of the planet, so it's even more favorable than we initially thought. These are the emission spectroscopy metric, but now separated in between channel 1 and channel 2 band passes from Spitzer. And yeah, it would be a really nice way to confirm or disprove this theory that TOI-24b would be an exposed Neptune mantle. So basically, just the take-home messages are that this TOI-24b object is a special case of a hot and dense sub-Neptune. We found hints at the poor heat redistribution on the planet and to a metal-rich atmosphere. And it forces us to consider the possibility that these sub-Neptunes, they might be more diverse than we initially thought, and they might not all be hydrogen-rich. So yeah, I guess that's, thank you.
Thank you, Pierre-Alexis. Do we have any questions for Pierre-Alexis? No questions? Going once? Going twice? Cool, sounds good. Well, thank you so much for the presentation.
Thank you.
Justin and Pierre-Alexis, these were great. So we're gonna end a little earlier today. We only had 2 TEPS trainees present. And yeah, this concludes the TEPS seminar. So we'll see all of you next month for the final TEPS seminar of the year, of the academic year. All right, take care, everyone.
Thank you. Take care.
Take care, bye-bye.